Our next natural disaster will be tsunami. Tsunami is the Japanese word for large harbor waves, and it is a very old term. Tsunami are different than normal waves, and they can technically occur in any body of water. We typically think of them as being associated with earthquakes and in the ocean, but they can also occur in lakes. And they can be triggered by anything that displaces a large volume of water. This can include movement of the ocean floor from an earthquake, but also a displacement of water from a landslide, or even an object falling rapidly into the ocean, like an asteroid. Let's start with the simplest version conceptually, where you can see what happens when a massive glacier calves into the ocean.
Mira, 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 mira. Ahora cae el de arriba, tiene que caer el de arriba. Sí, cae. Mira, mira, ahí está, mira, 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 mira. ¡Mira! ¡Mira! ¡No está llegando! ¡Ay, no se está! Chicos, ya lo estamos filmando. ¡Ay, qué lindo!
¿Estás filmando?
Lo filmé. Ya lo filmé.
Mira la ola.
Viste que ya te dije que teníamos que quedar. ¡Qué pedazote! Y están esas paredes están medias ahí, mirá cómo están. No. Mirá allá.
Mira acá cómo hace acá. Mira cómo hace acá.
Sí, cae. Mira cómo cae, mira. Sigue todavía, vos.
When earthquakes occur underwater, they can rupture and disturb the ocean floor. The movement of the ocean floor itself means that all that water above the ocean floor is also going to be displaced. This is somewhat similar to what's happening when that glacier calves into the ocean. This video shows what that rupturing process might look like, and it also shows how a sudden movement of the seafloor can actually lead to waves happening at the surface of the ocean.
Earthquakes are caused by the movement of the huge tectonic plates that continents sit on. And what happens is they come together, and one, in this case the Pacific plate, is moving below the Japanese or Eurasian plate. Now it causes that plate to bend when it sticks there. There'll be a bit too much friction, it'll stick, pressure builds up until suddenly it's released and flick. Have a look at this. Now this is the tectonic plate that Japan is sat on, and here's the Pacific plate coming down underneath it. Now normally they want to move together at about 9 centimetres a year, but sometimes they get stuck. And when they get stuck, the energy of them moving together gets translated to strain energy, literally flex and bend in these huge slabs of rock. Now that energy builds and builds, they're flexing and bending more and more. When they finally slip, that stored energy, all that twist and bend in the rock gets released into sudden movement, like that. As you can see, it literally flicks up, moving the ocean floor above it, which moves the ocean, causing a tsunami. So here we've got a bigger submarine version of what's going on. Now this gives a representation of what's been happening 24 kilometres below the ocean surface in the Japan Trench. Now these things work in what they call a stick-slip way. Most of the time they're stuck, but occasionally they slip. And that's what an earthquake is. So we've got it here, this is bent up here. It's full of pent-up energy, waiting to slip. Now when the slip happens, that energy gets released into the ocean, causing a series of tsunami waves, moving in both directions across the Pacific.
After an earthquake happens and the seafloor is disturbed, that huge volume of water moves in multiple directions away from that displacement location. This leads to what are called distant and local tsunami. Typically, the land nearest the earthquake is impacted very quickly. That is the local tsunami, whereas the land further away on the other side of the ocean will be impacted only if the tsunami is large enough to travel all the way across the ocean. This is called the distant tsunami. For the tsunami to travel all the way across the ocean, it would typically need to be triggered by a magnitude 9 or other very large earthquake. As you can imagine, the displacement from an earthquake this large is going to cause a huge local tsunami. This is exactly what happened when an underwater earthquake happened near Japan in 2011. The waves from the tsunami traveled all the way to the west coast of North America, but this distant tsunami was relatively small. The local tsunami waves hit Japan nearby and caused a lot of damage. This National Geographic video described what happened with that earthquake and tsunami in Japan in 2011.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. When two tectonic plates push together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11. And a rare view from the air, video of a tsunami wave approaching the shoreline. In Japan, some tsunami waves reached as far as 3 miles inland. Japan may be the most seismologically studied country in the world, and with more than 1,200 high-precision GPS stations, a geophysicist at the University of Alaska used the data to create a visualization of the March 11 quake. The waves of displacement that you see were moving as fast as 5 miles per second. In this photo, the ripples of tsunami waves are seen moving upstream in the Naka River at Hitachi-Naka City. New technology left an enormous amount of visual evidence for study in years to come, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future.
Tsunami are characterized by features of the waves. Waves have two features, wave period and wave height. Height describes the distance from the trough of the wave up to the crest of the wave. It is basically how tall the wave is. Wave period is the time between two wave crests, or between two wave troughs, which should be similar. Generally, tsunami are described by their height, but the wave period is important to look at as well, because it tells you how much time you have until the next wave. As the wave moves into shallow water, both wave period and height change. In the deep water, the wave is not very high. The period is somewhat long, and the wave travels very fast. As that big wave moves into shallow water, the wave height gets taller, the period gets shorter, and the wave slows down overall. So if you were in a boat out in the middle of the ocean, would you notice a tsunami wave? Take the poll over on the side of the lecture. Why does this happen? As the wave gets into shallow water, it starts to drag along the bottom, which slows it down. But there is still a lot of water moving. In the image, the amount of water originally moving was 4,000 meters or 4 kilometers of water. But now we are squeezing this large amount of water into a shallower space, so the wave has to get higher. And that faster moving water offshore is still coming in, so it quickly catches up, making the wave occur more frequently. Bays also act to amplify tsunami waves in a similar way by squeezing them into a smaller and smaller space, making the wave height much greater. An example of this was in Indonesia in 2018, when an earthquake that didn't really cause a tsunami anywhere else caused a huge tsunami wave all the way down at the very end of this bay here, where the wave height reached 10 feet. We identified tsunami using water level data. This is water height from Hawaii following the Chile earthquake in 2060 that was approximately 9.5 magnitude. You can see that before the tsunami hit, water level was basically about 0, which was their approximate low tide level. Then the first wave of the tsunami came in and the water level went up 5 feet. Then the water level actually went quite low, almost 3 or 4 feet below the normal water level. And then there was a second, much larger wave that was about almost 10 feet high. And the water got even lower again. And then a huge wave came in that was over 14 feet high. So the first wave of a tsunami may not be the highest wave. And often a large portion of the beach is exposed before that really large wave comes in. You can also see how frequently these waves were coming in. There were basically up to 3 waves over a 30-minute time period. So the period of the waves coming in Hawaii was about every 10 to 15 minutes. Here's an example of the travel times and wave heights from the 2004 tsunami. You can see that this hits Indonesia very quickly, and only much later does it hit the other coasts. Also, the waves are smaller the further away they were from where the tsunami started. And up in the Bay of Bengal, the waves were very large, over 10 feet high, as that water got squeezed up into the bay. So what did we cover? Tsunami are caused by anything that displaces a large amount of water. The size of a tsunami wave depends upon a variety of factors, and this includes the amount of water that was displaced originally. Also, how close you or that location where you're at is to the event where the wave actually started. And then finally, the shoreline depth and the shape, which influence how high the tsunami can get as it approaches shore.